Hey there! In this video, we are going to talk about systems of nonlinear equations and systems of inequalities. First up, we're going to look at nonlinear equations. Now, our systems can look vastly different depending on what those equations look like. Here I have three examples of what solutions might look like if you have a parabola and a straight line as your equations in your system. So before we've got used to with all the systems we've solved, there was one solution, there was none solutions, or there was infinitely many. Here I can see there's a wider variety. I could have no solutions where the two graphs never intersect, like on the left. I could have exactly one solution, like the example in the middle, or I could have two, like the example on the right. And depending on the look of the equations, potentially even more than that. So you want to keep that in mind and make sure you're finding all the solutions when you're working with nonlinear systems like this. So let's look at an example. Here I can see this is much different from what we've done previously because I have an x squared in one of my terms. So it's probably looking like one of the examples of the graphs that we just looked at. You can graph these to get an idea of what your solutions look like, but we're going to solve these algebraically today to make sure that we can do that as well. So the methods we've learned to solve these algebraically is either the addition method or the substitution method. Substitution tends to work out a little nicer with these, and that's what I'm going to use here, particularly because both of these equations are solved for y. So it's easy to do a quick substitution of one into the other. So if y is equal to 2x, according to the second equation, then I can replace the y in the first equation with 2x. And that gives me 2x equals 3x squared minus 1. And from there, well, that's a quadratic. So I can solve that like we have many times before by moving everything to one side of the equation. I'm going to subtract 2x from both sides. So I get 0 equals 3x squared minus 2x minus 1. And I can try and factor that, or if I don't feel like it, I can go straight to the quadratic formula, which is what I'm going to do here, just for the fun of it. Okay, so if I plug everything into the quadratic formula, remember that formula is negative b plus or minus the square root of b squared minus 4 times ac all over 2a. So I plugged everything in, and from here I'm going to simplify it. So I'm going to end up with 2 plus or minus the square root of 16 over 4. And the square root of 16 is, or sorry, over 6. The square root of 16 is 4, so I get 2 plus or minus 4. Over 6. So 2 plus 4 is 6. So I get 6 over 6 is 1. And 2 minus 4 over 6 will give me negative 1/3. So I end up with those two solutions. This would have factored, but if you don't like factoring coefficient or quadratics with the leading coefficient that's not 1, you can always use the quadratic formula. So I found two solutions. That tells me that the line intersects the parabola twice. And I've only found the x, though, of each of those solutions. So I need to go back to the original two equations with my two solutions and plug them in to find the y's that would pair with them. So starting with the first one, if I plug in the first solution of x equals 1, I plugged into the second equation because it's simpler. So y equals 2 times 1. So I get a solution of 1, 2 for that first one. And then I'm going to plug in the negative 1/3. And that'll give me a y value of negative 2/3. So my two solutions are 1, 2, and negative 1/3, negative 2/3. And again, you can always verify this by looking at the graph and by plugging them into the original equations to test them. So that's how you're going to usually go about solving a system of nonlinear equations. The other thing we want to talk about in this section is systems of inequalities. We're back to straight lines with this one, but now there aren't equal signs, they are inequalities. So to solve these, we're only going to solve them by graphing because it's not a single point anymore. It's going to be a region on the graph. And those can be hard to describe mathematically, but graphically is much easier. So how we're going to solve a system of inequalities is we're going to graph each equation, and then we're going to do a test point for each one and shade the region because it's going to say something like y is greater than. It means that when you graph that, then one of those halves that the line splits everything into is going to be solution, everything on that side. So you just have to figure out which side is the right side. You might intuitively be able to look at and figure it out, but testing a point is always a great way to verify and make sure that you're shading the right region. So you're going to do this with each line. Something to remember, if your inequality has a less than or equal to or a greater than or equal to, then you will graph that as a solid line because the line itself is part of the solution. If it's a strictly less than or strictly greater than, then you're going to use a dotted line because the line itself is not part of the solution. It is the boundary of the solution. So let's look at an example. Here I have a system of inequalities. Y is greater than 2x and y is less than or equal to negative x plus 2. So I'm going to start with the first one. Y is greater than 2x. I'm going to solve it, or I'm going to graph it just like it was in a y equals 2x. Only I'm going to use a dotted line when I graph it. So there's my y is greater than 2x, but I still have to figure out which region to shade. Should I shade the top half or should I shade the bottom half? And if you can look at it and figure it out, that's great. But if you're not sure or you want to verify, it's always a good idea to pick a point. So I'm going to pick any point that's not on the line. So I could have picked one on the top or the bottom. Here I'm picking the point 0, 2. It's clearly not on the line, and it's clearly in one of my two hemispheres here. And I'm going to plug it into the inequality and see if I get a true statement. So if I plug it into y is greater than 2x, that gives me a 2 on the left and 2 times 0 on the right. And well, 2 is greater than 0, so that's a true statement. So the side with that dot is the side that I shade. So that is the solution to just the first inequality. That's what its graph looks like. Now I'm going to repeat all this process on the same set of axes with the second equation, and where the two regions overlap is my solution. Okay, so now I'm going to graph the line y equals negative x plus 2. And I'm using a solid line this time because the inequality is a less than or equal to. And once again, I'm going to pick a point. Here, 0, 0 is a great one to pick, and it's definitely not on the line that I'm working with right now. So I'm going to use that one, plug it into the inequality, see if I get a true statement. So if I plug in 0, I get 0 is less than or equal to negative 0 plus 2. Well, that gives me 0 is less than or equal to 2, which is true. So the side with that point is the side that I shade. Okay, so I have my two inequalities graphed and shaded, and where they overlap, so this region here on the left where they overlap is the solution to the system.